Phil Physiker tosses a ball across a field. We show sample positions of the ball at 5 locations: A, B, C, D, and E. We draw a vector at position A to show the initial velocity of the ball. At this position, the ball has just left Phil's hand, so no further throwing force acts and remains with the ball. Once out of his hand, the only force on the ball is that due to gravity and the force of air resistance. To make the physics clear, we'll assume air resistance can be neglected. This vector has 2 components: a vertical one that changes due to gravity, and a horizontal one that remains unchanged as long as no horizontal forces, such as air resistance, act on the ball. At position B, we draw a shorter vertical component due to the loss of speed going upward. It's shorter than the component at A. But the horizontal component is the same as at A. We construct the resultant velocity vector at this point. At position C, at the top of the path, the vertical component has shrunk to 0. Only the horizontal component remains, which is then the vector for velocity at this highest point. Note that its length is the same as elsewhere. So how fast does the ball travel at the top of its path? 0 if tossed vertically. At other angles, velocity at the top is the same as the initial horizontal component of velocity, and the horizontal component at other positions. At position D, we have much the situation as in B. Same size horizontal component, but with the vertical component directed downward. So the resultant of these components gives the velocity vector at D. Note it's sort of an upside-down image of the situation at position B. And finally, much the same at position E. We're off the page here, but you get the idea. What we have is an upside-down version of A. The shape of the ball's path is a parabola. With air resistance, the path is not parabolic. It's something like this. The horizontal component in each successive position becomes smaller due to air resistance. We just show the horizontal components here. These smaller components are why the ball doesn't go as far downrange. And air resistance vertically means the ball doesn't reach the same height. Interesting? Let's get back to our ideal case without air resistance. The vectors we show are velocity vectors. We could also draw vectors for force, and even vectors for acceleration. Let's draw a vector for the force of gravity acting at the ball, say at position B. Shall we find the resultant of the velocity and force vector, say with this parallelogram? And what would the result be? The answer is nothing with any physics meaning. It would be rubbish. Don't do that. You can't combine velocity vectors with force vectors. They're different animals. To distinguish the two, we show force vectors in red and velocity vectors in blue. Phil Physiker says it well.
Take care with velocity and force vectors on the same diagram. They don't combine.
These red vectors represent the downward force of gravity on the ball all along the path. Although velocity varies along the path, we see that the force of gravity does not. It remains constant. The force vector is the same at all locations. Velocity vectors are one thing, force vectors are another. I want to lead up to a concluding question. We could as well have drawn acceleration vectors in this lesson, but we didn't. And a little thought will tell you that they'd compare well with the force vectors. After all, force and acceleration are directly proportional. Here's my question. What would an acceleration vector look like at the top of the path at point C? What would be the acceleration of the ball at this highest point? Think carefully about that. Until next time, good energy.